This is how I picture a transformer. You have the transformer right here, which I represent as capital T. Then within the transformer, you have blocks. Like this is one block, this is another block, here's another block. And each of those blocks consist of a normalization layer, a attention layer, and a multi-layer perceptron. So the multi-layer perceptron is what people typically think of as a neural network. You know, the dots with the lines connecting to other dots and so on, etc. So that's what people typically think of as a neural network. Is like this is a example of a multi-layer perceptron if it has, you know, multi-layers, so on. So that's what this part is. And the attention mechanism right here, it consists mainly of queries, keys, and values. So there's queries, keys, and values. And the queries are kind of like if somebody's wanting to look up a phone number for, just say, one of their friends in the phone book. So the query would be like, okay, I want to look up, just say, I'll make up a common name, George. I want to look up George's phone number. The keys are actually finding the name George in the phone book, and the values is the actual phone number. That's one analogy of how the queries, keys, and values work. The mechanics of it, a lot of the mechanics of it in detail are the same as the multi-layer perceptron. It consists mainly of things called dot products. Dot products fundamentally are just multiplication and addition. And you can have matrix multiplication, which is just doing multiple dot products sort of at the same time. So anyway, inside the transformer block, you have a normalization layer, which sort of squishes the numbers down so they don't get too big. You have a attention layer or attention mechanism that connects how the words are associated with each other. And you have the multi-layer perceptron, which one way to think of it is it starts pulling more meaning out of words or representing more meaning or richness within each word. And so basically this is the richness of the word, each word, and this is how the words are related to one another. This part's just the squishing the numbers down so they don't get too big. And you can reorganize the normalization in different ways. So now I'm going to go to the GPT-2 code and show some of how that works. So this is the tokenizer. Well, I'll go line by line partly. So here's where you import torch, tick token, garbage collector. This is for efficiency. And the GPT-2 model, this is the pre-trained GPT-2 brain cells, I guess is one way to think of it. So right here it says if torch.CUDA is available, or dot is available, CUDA, else CPU. So this is checking if the graphics card is available for processing the data, because it has a lot more cores than a CPU does, so it can process more at a time. And here's the GPT-2 model, and it's putting the stuff on the device, like the graphics card with CUDA. And here's the tick token for converting the words you type in into numbers representing those words. It sort of breaks. You can think of it as you type in words like down here, like the Golden Gate Bridge spans. So type that in, and then it'll be broken apart into things called tokens. Just say, to simplify this, if each word is a token. So the is a token, golden is a token, gate, etc. So what the attention mechanism does right here, it will go to the where it says the Golden Gate Bridge. It'll just say, for example, the word golden, it'll look at itself and the word before it and be like, how is the word before me representing what I am? And the word gate, it'll look at each word before itself, be like, the golden gate. It'll look at itself too. So it'll say, my word is gate. So each word before me gives me meaning. So by gate, it could be, if it was just the word gate, it could be talking about a gatekeeper or whatever. But it sees the word golden right before it. And so it could be, okay, this is talking about a gate that's gold. And you go the word before it. And it could be like, okay, it's talking about not just a gate that's gold, but it's talking about probably a bridge. And so it's looking at itself and each word before it to get its own meaning. This is the attention mechanism right here. So the word bridge, it'll look at itself and each word before it. It'll be like, the golden gate bridge. And it'll be like, yeah, I can understand now what it's talking about. The word spans will look at the stuff before it and think, okay, now I know the direction more that this is heading in. So I'm going to use this information, and based on the patterns that I've learned through looking at a whole bunch of words and how they connect and the meanings of them, I'm going to predict what the next word is. So in this loop, it will go down here and input the prompt, which is converted to numbers with tick token. It'll input the thing in the raw forward, which is a function that's up here. And it'll put it on the device, which is, if it's a graphics card, would be CUDA in this case. So I think it's typically CUDA. So this is putting the tokens representing the Golden Gate Bridge into the raw forward, which is code that's up there. And then it outputs its prediction for the next word. And you can see, as you can see down here, it predicted based on the Golden Gate Bridge spans, which is written up here, that the next word should be the. So it would output the word the. Then it would append or attach it to the end of this list of words up here. Well, it's still in number form, but it would attach it to the end of here. So it would be number representation of the Golden Gate Bridge spans the. Then it'll loop through again with that phrase, the Golden Gate Bridge spans the. All of this. It'll then go into the forward, and it'll process and predict the next word, which is san. And then all of that will be in this list because it'll append san to this list. And all that will go into the raw forward and predict Francisco is next, and so on. And it'll do that 20 times because it's using a for loop and it's set to do it 20 times. So if I go up here and look at the raw forward, just glance at it for now, it takes in tokens, which is what was shown earlier, and you can ignore this stuff currently because this is for the controlling the AI through with a sparse autoencoder and stuff to do with that. But just look at the word or the parameter tokens. And so it takes in the token, like showed down there earlier, which is the tokens, which is the list of words in order, like the Golden Gate Bridge spans. And then it will come in here and process through here's the layer. Whenever I say layer, this is what it's talking about. The transformer block, it's also known as a layer. And remember, this block is right here. and it'll eventually pass through another block, which is just the same pattern. It's just sort of like filtering as it goes through each block, but they had the normalization, attention, and the multi-layer perceptron in them. So once it goes through here, there's the normalization, the N right here. There's the QKV, which is queries, keys, and values, and that's what I was talking about earlier, which is right here in the attention mechanism, the QKV, like the person wanting to call their friend, and so they look up the friend's name in the phone book, and then they find their number and call them. So that's like the queries, keys, and values. And right here it says QKV. So these are the weights for it, and these are the biases for it. Basically the connections between the brain cells inside the illustrations of the dots and lines connecting to other dots and so on. So it's like each of these dots is a brain cell, and the connections between the brain cells is mainly what gets adjusted so that it can learn. Like adjusting this and so on is how the AI learns. So this is what the W is. It's the connections, like this connection and so on. And so the bias, it's one thing that adjusts certain stuff within there. It's adjustable also, but the key things is usually the weights. Okay, so this breaks apart the queries, keys, and values. So if you look up here, it says QKV. They're all packed together. So what this is doing is it's unpacking them, because the queries are first, and it's 768 numbers long, and the keys are the next 768, and the values are the next 768. It's doing sort of the same for the biases as well. And so it's matrix, or it's matrix it depends on how it's structured. If it's batches, I believe if it's batches, then this is matrix multiplying the output of the normalization with the queries, keys, and values. And so this is taking the batch, I believe it's the batch size right here, which is how many groups of stuff's processing at once. I think that's how it works on that part. Anyway, and this is grabbing from the beginning of the queries, keys, and values weights up through 767, because it starts at 0. So that's 768 things. Because if you start at 1 and go to 768, if you start at 0, then you can go to 767. So this is like a stop sign, like you stop before you get to there. Then this grabs the next 768 items, and this grabs the next 768. So that's the queries, keys, and values, the matrix of them, and it's multiplying with this to assign to here. So then go down here and break it apart into the multi-head. That's something that's a little bit more complex, but you could think of it as each of these heads is sort of sectioning it off. So section off the queries, keys, and values into smaller pieces, so that each piece, or each of those smaller pieces or smaller chunks, can process different types of data at once, and later they get combined back together. So if you look at the attention is all you need paper, then you would see a equation similar to this in there, and that's part of the main equation for the transformer's attention layer. It's the queries matrix multiplied with the transpose of the keys, and divided by the square root of the dimension head. or the D head. So this is a mask for what's called causal attention, because remember earlier I was saying for it to predict the next word, like in the Golden Gate Bridge spans, it's supposed to predict the is next, and it puts all that in here in the raw forward again, and it predicts San is next, puts that in the raw forward and predicts Francisco is next, and so on. But when you're training it, but if you put, like when it's being trained, if you don't zero out or sort of zero out the future things, then it already sees them. So it's not necessarily learning to predict, it's just looking at the answer. It's like somebody taking a test and look at the answer while they're taking the test. So that's what the causal self-attention is. That's what the mask is doing, is it's blocking out the future things so that it can predict them instead of just looking up the answers. And this is a softmax that turns everything into a probability distribution where the sum of all the values is equal to 1. Just say if it's 3 different options for whatever it's trying to predict, cat, dog, mouse. Just say if the cat is 20%, dog is 40%, then that would also mean the mouse is 40% because the total has to equal 100%. So 20 plus 40 plus 40 is 100. And so that's partly what the softmax is doing, is converting to a probability distribution. And later, after it passes through a bunch of this stuff, then the output, if it's deterministic, then you can input the same words over and over and you'll get the same result. But you can also use a thing that picks randomly based on the percentage of the probability output of softmax. If you want it to be where you can type in a phrase and it outputs something, and then next time you type the exact thing and it outputs something else. That's what things like ChatGPT and so on, you can type in a question and it'll answer, and you can type in a question again and it may answer slightly different. And that's partly because it's using that that thing that selects somewhat randomly, but the probabilities of what it selects, like the next word or token, is based on the output probabilities of the softmax. So here the pattern, which is carrying the scores, the query's keys, it's carrying those are called that's called the attention scores. It's matrix multiplying with the values at that point. It's matrix multiplying with the values at that point, and then it transposes and converts it back to the original length. Because remember, when it broke apart into attention heads, it was like breaking apart into smaller chunks to process different concepts. Right here is where it connects everything back together again. So then it goes down here, and this part right here is the residual connection, which in the back propagation, whenever it's learning, it helps prevent what's called vanishing gradients. And that's some other topic currently. It's not within the scope of this video, because this one's focused on mainly the forward pass of GPT-2. So anyway, you add this residual connection to here, and it also helps it process more efficiently as well. So you add this X, which is up here, to the result of these calculations all through here. So basically how I picture it is you take this X and you go and spin it around or loop it around to here and just plop it on the end after all this other calculations are done with the queries, keys, and values and so on. Then that creates this X, And then you pass it into the normalization layer again to squish the numbers down so they don't get too big. And then you pass it through a multi-layer perceptron. That's what, see, this is the multi-layer perceptron, which is right here. And that can give more understanding of the meaning of each word, is one way to conceptualize what that part does, the multi-layer perceptron. And it's more specifically, well, part is kind of mixed together, but this is parts or whatever, the multi-layer perceptron. The FC means fully connected, and that's when you see a neural network with the dots and lines and so on. It fully connected means that, like, this dot is connected to this one, but this dot is also connected to that one. And this first dot is connected to down here, and the second dot's connected to down here. Everything's connected to each other, so that's fully connected. Everything's connected to each other from one layer to the next. So that's what the FC stands for. And then again, you add the residual connection and come down here and see, where is it? This part is for controlling the AI. It's not necessary for this video. And here's layer normalization again to squish down the numbers again. Then it takes the weight token embeddings that was from before, and it transposes them to convert to the right shape again, and it matrix multiplies the output that just got squished down with this so that it converts it into the logits or logits, and this ends up being the prediction, which would be, like, for example, a giant list of numbers or a vector of a tensor vector, or however you want to call it, or whatever you want to call it, with lots of numbers in it. It wouldn't be probabilities unless you convert it, just say, through softmax, but you're, in this case, interested in predicting what it's most likely the next word, so it would just be the highest value here, like in this version of the inference. And that's what the argmax is. So what the argmax will do is it'll take the float value, like this is a giant list of numbers. It'll take the float value, it'll find the location with the highest number in it, which is the prediction of the neural network, like its highest prediction. And it'll say, where is that location with the highest prediction? And the location is saying what token or what word is this. Like, just say, hypothetically, if the location 1 or location 0 is the word cat, and location 1 is the word dog, and location 2 is the word mouse. If it was going to predict the word, or if it showed the highest probability or the highest number from the logits in location 1, you know, location 0, 1, and 2, if it showed the highest number in location 1, then since location 1 represents dog, then it would say location 1.item, or the argmax, which would be the number 1. So this just basically pulls it out of the tensor, the item. So it would just be the number 1, and then it would append it up here. So it would predict, in other words, that 1 is the next token. And remember, 1 represents dog. So it would be basically saying that dog is its prediction for the next word. And so then it could attach it to here and then process the stuff through the raw forward again to predict the next word. But in this case, once again, the Golden Gate Bridge spans. So it found that the highest number was wherever location for the word the is. So it got that number, and then it predicted that's the next word, so on. So anyway, that's, oh, and last part, it then, once it breaks out of this loop after the 20 iterations, then it takes that list and it uses the decode to convert it back into text, and that's how you see the Golden Gate Bridge spans the San Francisco Bay Area, etc. So that's how GPT-2 works, and that's fundamentally how most, or almost all learned language models work, such as Claude, Grok, ChatGPT, BERT, etc. So anyway, if you have any questions or comments, let me know, and thanks for watching, and please click like and subscribe. Thanks.